Good morning, ladies. Today we are looking at the last bit of work on gases. So we are comparing ideal gases with real gases. Let's just take a look at our graphs again. And for now, just look at the black lines on the graphs. So Boyle's law, you know that we said that pressure and the inverse of volume are directly proportional. So that's the black line over there. Pressure and volume are inversely proportional, and pressure times volume gives us a constant answer for a specific set of results. So there's the constant line there. And according to Charles's law, we said that volume and temperature are directly proportional. So that is the line that we saw over there. Now, one thing that you need to understand, all the graphs that we have drawn up to now are relevant for an ideal gas. This is a hypothetical gas that obeys the gas laws. So if I had to go look at these graphs for real gases, I will find that there are deviations, and this is the next thing that you need to know. Real gases deviate from the ideal gas under two conditions. And you need to know these two conditions, and they are at high pressures and at low temperatures, real gases deviate from ideal gas behavior. So if we go back to our graphs, you can see over here at high pressures, there's actually a deviation here. So the red line is what the graph will look like for a real gas. Even here, the red line is what it would look like for a real gas. Same thing over there, same thing over there. And the reason why is what we need to look at as well. So we said real gases deviate from ideal gas behavior at high pressures and low temperatures. Now, what is the reason for this? That is the next thing that we need to look at. And we find that there are two reasons why real gases deviate from ideal gas behavior. According to the first one, the molecules of a real gas occupy volume. They do have volume. Compared to that, if you go look at the very first lesson that we did, where we looked at the properties of the ideal gas, one of the things that we wrote down was this: the particles are very small and together do not contribute to the volume of the gas. The gas volume is determined by the volume of the container only. So according to this, ideal gas particles don't occupy volume, but we know that real gas particles occupy volume. So if we go back to our graphs and we look at this one, for example, at very high pressures, your real gas will occupy more volume compared to the prediction of the ideal gas, because ideal gas particles don't occupy volume, but real gas particles do. And even if you look at Charles's law, according to the line that we drew, this original graph over here, at zero temperature, this gas occupies a volume of 0. So it doesn't occupy a volume at all. And we know that that can't be possible, because it doesn't matter how small the gas particles are, they do occupy volume. And that is why here you can see that at very low temperatures, your real gas will occupy some volume compared to your ideal gas prediction that says at zero temperature, the volume occupied is 0 as well. Then the second reason for the deviation is this: there are forces of attraction and repulsion between the particles of a real gas. Again, if you go back to your ideal gas properties, we said that the molecules of an ideal gas exert no forces on one another, nor on the sides of the container, except when they collide with each other or with the sides of the container. So our ideal gas particles don't exert any forces on each other, but real gas particles do. And when are we actually going to see these forces of attraction? they become relevant at very high pressures, because what happens at high pressures, we are forcing the particles closer together. So what is going to happen at very high pressures, you actually find, because the particles are closer together, the forces of attraction do become relevant, and it affects the behavior of the gases. Okay, that brings us to another question. Which gases will deviate the least from ideal gas behavior? And the answer there is the gases that consist of the smallest molecules, the smallest particles. They will get the closest to ideal gas behavior, because we said that the particles of the ideal gas don't occupy volume. So gases with the smallest molecules, the smallest particles, will come closest to ideal gas behavior. And that is why we say that smaller, simpler molecules such as hydrogen or helium are the gases that will deviate the least from ideal gas behavior. And then over here, what happens to real gases at very low temperatures? Now, this is actually where the forces of attraction are relevant, because real gases at very, very low temperatures, they liquefy. So what happens is there's a decrease in their average kinetic energy. There's a decrease in the speed of the particles. The particles are going to move closer together, and the forces of attraction become relevant, and that is why real gases at very, very low temperatures, they liquefy. According to the ideal gas, there are no forces of attraction or repulsion between the particles. So you might wonder, why do we then actually use these gas laws if they apply to this ideal gas? And the answer is, under most conditions, real gases behave like we describe in our gas laws. It's only under extreme conditions, like very low temperatures and very high pressures, where real gases deviate. And even the conditions that we have in a lab, we can't reach those very high pressures and low temperatures to actually even see the deviation. So that is why, despite the deviation of real gases from ideal gas behavior, we still use the gas laws for everyday conditions in the lab. Right, and that is then the end of this section. So that means that we've got chapter 7 revision questions on page 153 and 154, and there's quite a lot of them, and that is why I will only post those answers on Wednesday to give you a bit more time to answer those questions. And because it's the end of a section, like before, there are also some exam practice questions, and you'll find them on page 156 to page 158. But those questions you can answer in your own time, and once we are back at school, we will do those or go through those answers together as part of our revision program. Thank you, ladies.